We know that computers have limited capacity for storing numbers, and certainly if you were to compare, let's say, the result of zero point 0.1 plus zero point 0.2, if you were to compare it directly with the result of zero point 0.3, you're in for a surprise because to us it may appear as though the sum is actually correct. But if you actually do it in MATLAB, so let's do it, not zero point 0.1 plus zero point 0.2 equals zero point 0.3, then we get a 0. So why is this happening? Well, the reason why this is happening is because we have only a finite number of bits for representing each of the numbers. And in fact, if you do the following, if we, for example, take 0.1 plus 0.2 and we subtract 0.3, we'll get a non-zero result. We get something like 5.55 times 10 to the power of minus 17. So essentially, there is a problem. We cannot really compare numbers like this, and this applies to pretty much any programming language. Instead, what we have to do is if we want to perform this kind of comparison, we have to rewrite it. We have to say that the absolute value of 0.1 plus 0.2 minus 0.3 is less than some tolerance value. And the tolerance value is strongly related but not equivalent to the idea of a machine epsilon. So essentially, the machine epsilon is a special number that any system will give you, whether it's MATLAB or C++ or something else. In MATLAB, it's EPS. For double precision, it gives us the following value. And what this means, essentially, is that when the numbers are stored in the computer, they're stored with about 16 digits of precision. So if you have a number that's close to 1, for example, it's stored with an error of around 10 to the minus 16, whereas if the number is, let's say, 1,000, it will be stored with an error of 10 to the minus 13, and so on. So essentially, the machine epsilon is not equal to this number. So the tolerance here really depends on the kind of calculations that happen inside the comparison, inside the functions that you are actually comparing, because the amount of error that can be accumulated through the calculations is really difficult to predict. We do have scientific theory that tells us how we can calculate approximate tolerance values based on the machine epsilon, but in practice what happens is you have super complicated algorithms that you write yourself, and it's simply not possible to use the machine epsilon to predict the overall tolerance, which is why in the real world most of these values, when you see values, tolerance values like this during the comparisons, they're typically experimental. And furthermore, and this is a bit disappointing, you will see differences in tolerance values that you need depending on even the compiler that you're using. Because remember, compilers try to optimize floating point calculations. They have different floating, and as a result, in the real world, the calculation of tolerance values is very much an experimental affair, although strictly speaking, especially for simple examples, you can try to derive actual analytical values, but in reality, we hardly ever do that. So the machine epsilon is certainly available to you, and it does give you an indication of the amount of precision that you're getting when storing numbers. However, it's of very little use when actually comparing the results of calculations.